Everybody, welcome to our next video in our Unit 0 Chem 1 review for Chem 2, which is all about naming chemical compounds. Now, by no means is this a way to name every single chemical compound that you'll encounter in any chemistry class, but this is a really good way to just name very basic chemical compounds that you hear about pretty frequently. I normally will name chemical compounds by using this flow chart. This is how I teach it in Chem 1. However, I don't want you to have to rely on this flow chart because I do think it's pretty easy to name these chemical compounds. So I did include this chart in that packet I gave to you just to kind of review and refresh your memory, but hopefully you won't need to use this all of the time, because there really are just three ways to determine the chemical name for a compound. So there's two things you really have to look for when you're naming chemical compounds. We're just going to go through this really quickly here, and then we'll do the sample problems together. The first one is if there's a metal present. And really, it doesn't matter too much if it contains only two elements because you're going to name them very similarly. Is there a metal present is what you have to look for first. And your metal, the metal that you're looking for, is going to be the first ion that's listed in the formula. And what you're looking for is if the metal can form more than one cation. So I believe, let me just take a double check here. In the packet I gave to you for over the summer, I gave you a very specific periodic table, and that periodic table shows you whether or not each metal can form more than one cation. I'm actually going to link my AP review video for naming down below because I have my Ziggy at home and I was showing you exactly what numbers to look at. So I'm going to link that below if you're not sure what I'm talking about, and you could see it down there. And I'll link it right at the time frame that you need it so you don't have to watch the whole video. But can the metal form more than one cation? If it can, so for example, gold has two possible charges. Gold can be a +1 or gold can be +3. Because you have those options on what charge gold is, you have to say gold's charge in the name. And that's because the formula could be two totally different things based on whether gold's charge is 1 or 3. So you do have to say what it is. So for one like gold, for example, let's write this down. So gold has the option of being +1, or it could be +3. You do have to say the name. You do have to say the charge on gold in that example. However, sometimes you're going to find that the metal does not form more than one cation. And a great example of that, actually right down here, which is sodium. So sodium is an alkali metal, which is present in group 1 on the periodic table. Because sodium only has one possible charge, its charge is +1, you don't have to say sodium 1 because it's always 1. It's inferred that it's 1 because there's literally nothing else it could be. So you don't have to say what it is, which is really the major difference between naming with a metal as your cation. So if it has more than one charge, you have to say what the charge is. If it does not have more than one charge, you don't have to say. Typically, you're going to find that these metals here that have more than one charge are primarily transition metals. Now, there are a couple of exceptions to that rule because zinc, for example, is a transition metal, but zinc only has one charge of +2. Silver is another exception. Silver is always +1, so you don't have to say whether silver is +1. But for the most part, your transition metals like copper and iron and manganese and vanadium, they all have multiple charges. Vanadium actually has like 4 or 5 charges. Manganese has even more than that. So these are if there's metals present. If there's a metal, you just say the name of that cation with a Roman numeral if it needs it. And then you just say the anion ending with "ide." If, however, you have a non-metal present, so these are for non-metals only. So non-metals only. You have to use prefixes when you're naming these. So it says, say the cation first, followed by the anion ending with "ide," and we want to use these prefixes to indicate how many of each element is there. So for example, if I have SO2, there's only one sulfur atom that's present. However, because sulfur is my cation, you don't have to use mono if there's just one cation here. So I'm just gonna underline this one here. And I'm just gonna say anions only. Your anion, of course, is that negatively charged ion. Anions only, you use mono. So sulfur, and then dioxide, because di is the prefix for two. So 2 oxygen atoms. For something like dinitrogen monoxide, N2O, you do have to use that prefix for nitrogen because there is more than one. Dinitrogen, 2 nitrogen atoms. You do use that mono for oxide in that case, because again, you use that mono for your anions only. Now, sometimes you might have a polyatomic ion present, and in that case, you just have to recognize the polyatomic ion, and I gave you that list of polyatomics in that review packet as well. You do not need to memorize polyatomic ions. I don't have them all memorized. I think you might just memorize them by chance because you see them so often, like nitrates, sulfates, carbonates, hydroxides. But otherwise, you do not have to memorize them. You will always have that list of polyatomic ions available for you. With that information, let's go ahead and dive into the sample problems in the notes where we name some chemical compounds, and then we write the formulas for those chemical compounds as well. So first, let's do sample problem 8, and we're going to name each of these compounds. Like I said, I want you to get comfortable with not using the flow chart, so you can reference that if you like and follow that appropriately. You can find out how to do that in that in one of the videos that I linked below, but I'm going to not use that in this case and show you how I would name these without having to look at that. So we're going to name each of these compounds here. And I'm going to do some of these, and then I'm going to have you do the rest of those on your own or to try them. So beryllium is a metal. So it is an alkaline earth metal. So because this is a metal, we're not going to use prefixes here. So do not go prefix crazy. You don't have to use mono, di, tri, whatever. Not necessary because I have a metal present. And in fact, beryllium only has one charge, and that one charge is +2. So you don't have to use a Roman numeral here. So we're just going to write beryllium. And then we're just going to name this polyatomic ion here. So if you look on your polyatomic ion sheet, you can identify what CN is. And that CN is what we call the cyanide polyatomic ion group. So the name of this compound is beryllium cyanide, and that's it. You don't have to do anything with this 2. The reason that 2 is there is because it actually comes from beryllium's charge, which is what we're going to do in sample problem 9 when we do the opposite of this, when we write the formula given the name. For B, let's see here. So B, you'll always look at this first element that's listed, and potassium is also a metal. So because we have another metal there, we don't have to use prefixes. We're just going to name this as I normally would, just saying the name of the elements that comprise it. Potassium only has one charge, and that one charge is +1. Don't have a lot of room here to write this down. Potassium's charge is always +1. It is an alkali metal with 1 valence electron. It's always going to lose that 1 valence electron. So again, we don't have to say the name. We don't have to say the charge on potassium because it is always +1. So we're just going to write potassium without a Roman numeral. And then we're going to say this name of the anion ending with "ide." If you look on that list of common ions in that binder I gave to you, it actually tells you how to properly change the ending if you're not sure. But you would change oxygen, so its ending is oxide. So the name of this compound is in fact just potassium oxide. No Roman numerals needed because potassium only has one charge, and no prefixes needed because there is no nonmetal as your cation. Next one here, so I have FeCl3. So Fe, of course, is iron, which is a metal. So I don't have to use prefixes here. However, iron does have multiple charges. Iron could have charges of +2, or it could have charges of +3. If you look at that gray periodic table that I gave to you, and if you look at iron's little box in there, right above the symbol, you'll see two numbers in bold. There is a +2 and a +3. That means that those are iron's possible charges. And again, if you watch the video I linked below, you'll be able to see what I'm talking about on that periodic table. Because iron has these two possible charges, we have to say what is iron's charge in this particular example. And the way you can tell what iron's charge is by looking at the subscript from the opposite ion right here. If you remember writing formulas in Chem 1, you'll remember that you actually have to switch those charges. So in this case, iron's charge has to be +3. So that's the Roman numeral we're going to use. So we're just going to say the name of the metal, which is iron. And we have to identify that iron's charge is +3. Then we just say the name of the anion ending with "ide." So in this case, we would just say chloride. Notice the difference between C and A and B. So iron has more than one charge. You have to say what the charge is with a Roman numeral. A and B, you don't have to because those metals only have one possible charge. Let's try D right here. So I have another metal, beryllium. We identified that up here, and beryllium only has one charge, so we can just say beryllium. So we'll write beryllium down. Now, a lot of times students get confused when they see the rest of this here. If there are multiple elements that are left over as your anion, most likely it will be a polyatomic ion. So what you can do is just identify what is this CO3 group. Look on that list of common ions and you'll see that that CO3 group is what we call the carbonate polyatomic ion group. It's a group of elements that has a charge, and because it is so common in chemical compounds, it has a name. It's called the carbonate group. E, a little bit different. So I have CCl4. I have carbon and chlorine here. This compound is nonmetals only. So this only has nonmetals. You should be able to identify that relatively easily just by looking at a formula. So there's only nonmetals here. Because we have nonmetals, we do have to use prefixes in this example. So let's go ahead and identify how many of each element is there and then use the prefixes as necessary. Notice that there's only one carbon atom in this compound, so there's one carbon. And like I said, you don't have to use that prefix mono if there's only one. So you just say the name of that element. So in this case, it's carbon. There are 4 chlorine atoms in this compound. So if you look on that flow chart, just to identify what the prefix for 4 is, the prefix for 4 is tetra. So we'll include that. And then you change the ending so it ends with "ide." So this compound name is carbon tetrachloride. Let's try one more together. So F, we do have a metal here. So I have potassium. Potassium is a metal. So we don't have to use prefixes in this case. Potassium is a metal that has only one charge. So we just have to say the name of the metal. So it's just potassium. Notice I have many different elements that are left. So if you want, you can highlight it, underline it, whatever you want, and look that up. That is, in fact, a very common polyatomic ion. This is what we call the sulfate polyatomic ion group right there. Like I said, you don't have to memorize them, but you might end up memorizing them just because you see them so often. Try to do the rest of these here. So try G through L on your own. Pause this video, and when you come back, I will have the answers here for you to check yourself. And there are your answers for F through L. So a couple of things I want to mention in terms of common mistakes that I see with these. The first one is K right here. So just beware that when you have nitrogen alone by itself as an element, that ending is nitride. So nitride, anytime you have an element, it always ends in IDE. That is not nitrate. That is not nitrite. Those are two totally different things. If you're not sure on how to change that IDE ending given an anion, you can always look on that list of common ions page, because I do give you the proper endings for that. For L, this polyatomic ion actually has two names that you can have. So this is not only bicarbonate, that's normally how I will name this. You can also call this cobalt-3 hydrogen carbonate. So just be careful. So just keep that in mind, because there are two possible options for naming that. Neither one of those is more correct than the other. They are both equally correct. Remember here, tin's charge is in fact 4. So it is tin 4 phosphate. And when you're naming something like this, like pentoxide, sometimes it's hard to kind of change the name of that, including the prefix. So penta, oxide doesn't really flow off the tongue as nicely, so the name of that would be pentoxide. If you have any questions on how to name those, just make sure you put a star next to them and you ask me when we come back to class, but otherwise that's naming. Let's go ahead and write formulas. So looking at sample problem 9, so write the formula given the following name. So you will have to reference your periodic table in addition to that list of common ions that's in that binder that I gave to you. So let's go ahead and write the formula for each of these. We have magnesium carbonate. So magnesium, of course, is Mg. And that has an overall charge of positive 2. Carbonate is a polyatomic ion, and that is CO3 with an overall charge of negative 2. So when we're writing the formula, we do have to switch the charges so they become the subscript for the opposite ion. So here, this 2, it's the absolute value, so you're not bringing the positive sign down, but just the number. This becomes the subscript for the opposite ion. And the same thing goes for carbonate's charge. This 2, not the negative sign, just the number 2, becomes the subscript for the opposite ion. So when you write this formula, we get Mg, so for magnesium, and this 2 comes down, so it's 2. And then I have carbonate, CO3, but there are 2 of them, so this 2 comes down. Now, we do have to write this carbonate in parentheses to show that there are 2 of this whole entire group. If I didn't include those parentheses, it would look like I had 1 carbon and 32 oxygens. That would be a really crazy compound. However, sometimes in chemistry, there's exceptions to rules. So here, look how I have a 2 and a 2. So this means that this is in a 2-to-2 ionic ratio. If you get the same number, or if you get numbers that have a, you know, they both go into 2, they're both divisible by 2, or they're both divisible by 3, you can in fact reduce this to the least common multiple. So instead of saying a 2 to 2 ratio, we're just going to say it's a 1 to 1 ratio. So this is magnesium carbonate, MgCO3. And you only do this step by reducing if it's ionic. So I'm going to make a note there. Reduce if ionic. And you know it's ionic because you have a metal bonded to a non-metal. You have metal and non-metal. So you don't have to always reduce it, because you don't have to when it is just comprised of only non-metals. You only do it if it is a metal and a non-metal. Let's try B. So copper 2 selenide. We do have a Roman numeral here. And remember, this Roman numeral means it's the charge on copper, because copper has multiple charges. Copper could be either a +2 or a +1. So we have to say what its charge is in this example. Copper's charge is +2. And selenide, so selenium is in the same group as oxygen on the periodic table. I believe it's below sulfur. So when we're dealing with binary compounds, you only have to determine how many valence electrons it has. So because selenium has 6 valence electrons in a binary compound, binary means 2 elements that make it up, selenium would have an overall charge of -2. So that's what we're going to use here. Same thing as before. Notice how this is a +2 and a -2, and this is an ionic compound. Because it's an ionic compound, those 2's reduce with one another. So your final formula is CuSe, just like that, CuSe. Nickel 2 chromate. So nickel does have a charge of +2. Nickel has multiple charges, so we have to say which one it is in this case. And chromate is a polyatomic ion. So let's get this stuff down. Nickel is a charge of +2. And chromate is CrO4 with a -2 charge. Now, I don't know why I did so many 2 ratios back to back with one another, but look, these 2's cancel out again, and because it's ionic, this happens to work out in this way. So your formula is NiCrO4. Nickel 2 chromate. Here's one where it's actually not 2 to 2, so that works out great. Lithium, notice there is no Roman numeral here because lithium only has 1 charge. It's an alkali metal, so its only charge is +1. And sulfate is SO4 with a -2 charge. So we do have to do a little switching here. Lithium's charge is +1, so that means that it becomes the subscript for sulfate. And sulfate's charge is -2, so that 2 becomes the subscript for lithium. So when we rewrite this, we get a final formula of Li2, because that 2 comes down, and we get SO4. So there's only 1 sulfate group here. And remember, you have to keep this whole entire thing together. You cannot replace this 4. That 4 can't go anywhere. It has to stay. What this 1 means is that you have 1 of this whole entire group. You have 1 sulfate group. Because it is 1 whole sulfate group, you don't have to write that SO4 in parentheses. If you want to, by all means do it, but it's unnecessary. That is your final formula. It is Li2SO4. Let's try E together as well, because this one's got a lot of numbers going on. So mercury, formula of Hg, and mercury's charge is +2. And that's what that Roman numeral is telling us, of course. And phosphate is a polyatomic, and its overall charge is -3. So we do have to switch some charges here. So this 3 is going to come down and become the subscript for mercury. And this 2 is going to switch and become the subscript for phosphate. Like I said, there's a lot of numbers here. So we're going to write this overall formula. And when I do that, I have Hg, mercury, 3, because that 3 came down. And I do need parentheses here because I am going to have more than one phosphate group. This 4 has to stay. This whole group is a phosphate. Without that 4, it is no longer phosphate, so you need that. And there are 2 overall phosphate groups. So that's the formula for mercury 2-phosphate. You cannot reduce anything here because your charges are 3 and 2. And of course, they do not have a least common multiple, so you leave it just as it is. We're going to skip a couple here and we're going to try I. So this one I want to do with you because we do have prefixes here. So there's prefixes because of course this is comprised of only nonmetals. So we're working with a covalent compound here. It's comprised of only nonmetals. When you're given these prefixes, so notice I have tetra, and I have tri right there. When you are given those prefixes, because you have all nonmetals in your formula, you do not have to switch any charges. I can't say that enough. All you have to do is write how many of each element are present. So for I, tetraphosphorus means you have 4 phosphorus atoms, tetraphosphorus, trisulfide. There are 3 sulfur atoms there. That's it. You don't switch anything. You just leave it as it is. These compounds that are comprised of all nonmetals are very different from ones that have metals. And that's because they have so many different combinations of charges, and the nonmetals get a little crazy with their charges. So you're going to find that they have very random combinations. Plus, we can form giant molecules with nonmetal compounds because they can bond in so many different ways. So leave it as it is. Also, you do not have to reduce anything with nonmetals. Notice up here, reduce if it's ionic, metals and nonmetals. You do not have to reduce if you have 2 subscripts where they are divisible by one another or they have the same least common multiple. Do not reduce them. It alters the Lewis dot structure. We'll get more into that kind of stuff when we talk about solids in one of the later units, but only reduce it if it's ionic. Anyway, I want you to try these other ones that are left. So these other 6, try those on your own. Pause the video, check your answers with me when you're done. I really don't know why I have so many 2-to-2 ratios in these problems, but whatever, it is what it is, so we're just going to go with it. F and G both have charges, both positive and negative for 2, so they do cancel out because they are ionic species. You have a metal that's present as the cation in both of those. Barium hydroxide, I think that one's pretty straightforward, as is silver sulfide. Silver is one of those transition metals that has only 1 charge. Dinitrogen tetraoxide. So like I was saying before, this is a molecular compound. This has covalent bonds in it. Because this is not ionic, you do not reduce this formula. So you leave it as it is. Dinitrogen is 2 nitrogen atoms, and 4 oxygens belongs to that tetraoxide. Notice here I didn't eliminate that A, but that's okay because I think sometimes it's like tetroxide, tetraoxide. Maybe you'll see a dash in there sometimes. It is what it is. So tetraoxide is 4 oxygens. Titanium 4 oxide. So titanium does have a charge of +4 in this case, and oxygen is always -2. When you switch those, 4 and 2 do have a least common multiple of 2, so it does reduce because titanium is a metal. If you have any questions on naming, you can always ask me, but I do have 2 other videos on naming, which I've mentioned I am going to link below if you would like to watch them for some different examples, and I do go more in depth with naming in there. But of course, you can always email me or ask me in person if you have any questions when we come back to school. So otherwise, I'm going to end this video here. Like I was saying, ask me any questions if you have them. Do not hesitate. Otherwise, I will see you in the next video in this review of Chemistry 1 in Unit 0. Have a great day. Bye.